Okay, pre-calc students, let's get this show on the road, folks. Okay, this first page is going to kind of tell you what's going on today. We're doing lesson 1-4. We're going to do the first objective, where we're looking at increasing and decreasing behavior of functions. So I want you to pay attention to the two key concepts in the book. There's one on page 34, and that involves increasing, decreasing constant functions, and what they look like, and description of them. There's also the key concept on page 36 that involves talking about relative and absolute extrema. And today I'm going to be walking you through basically how to do the kinds of problems in examples 1-4. Also, we're going to be using the study notebook, this page here, and first thing you're going to want to do is to copy in the objectives. And if you want to copy in these, that's fine too. It's basically what we're doing. Just add in there on number 2 when it talks about average rate of change. We're talking about slope. I'm going to try to refrain myself and not go into that too much today, but we'll get into that as we go along. It's a really important subject. Also, at the end, you'll be doing study notebook page 9 at the bottom, the active vocabulary, as the first part of your homework. I'll do that with you. I'll let you fill in the little picture there, and then at the very end I'll show you what the right answers are for that. So this might be a good place to pause so you can look at that screen, or you can copy them down from your book under the Now section on page 34 at the top. And then, yeah, in about 5 seconds I'll start going on with the next thing. Okay, here we go. Now, if you looked at that key concept there on page 34, you see basically all they're saying is look at this function in between these two spots and determine whether the slope is going up or the slope is going down or the slope is going flat at in between these things, generally in that area on the curve. And I don't think that's too terribly complicated. Increasing just means slope's positive. Decreasing means slope's negative, and constant means the slope is 0. Now what we're going to do here is kind of give you a preview of where we might end up at the end of the book. I'm going to give you this equation right here, the blue one, and you can see there that that's an x cubed. Now, if you're doing something like an example 1 type of problem, you're supposed to describe the behavior of that graph as you read it from left to right, as it starts down there at the bottom and goes through the middle and then zips off the top. So it's easy to see that and on a lot of graphs. This one's not so bad. It seems to be increasing the whole way. But what I've done is if I've gone in and I've made another equation that's called the derivative, or f1 prime, of the blue equation, and basically the red picture is a graph of the blue picture's slope. That is, you can see there that the red graph here, it's positive. It's in the positive function area all the way until we hit 0. Okay, and the blue one is increasing on that whole interval up to there. And then at there, the slope is 0, and the parabola reaches the point at the bottom. And then it begins to, it stays positive all the way up as you go. And that's because the blue curve there is increasing, and it increases more and more as you go from left to right. And that's why the red line, the graph of the slope of the blue line, is stays in the positive direction and gets more and more positive as you go across. Now, we've looked at some of those kinds of things already in physics. So it's really important you kind of get used to thinking of it that way. Don't look at the parabola and think it goes down and goes up. Think of that it's positive everywhere, and that tells you something about what's going on with the blue line. It's increasing on the whole interval. Some places it's not increasing as much, but through the whole interval it is increasing. It's going up the whole time. Now, obviously, not all graphs are as nice as that one. Some wiggle all over the place, and you're going to have to look at them and evaluate them this way. This one is increasing all the way up to this point right here, and then it decreases until it gets all the way down to here, and then it's increasing again. And what your job is in some of these is just to identify where it's increasing, where is it decreasing, and just indicate the interval over which that is occurring. So this is actually number 21 out of your problem set. And I'm going to use this one to explain the next concept. You're going to have some things that the book calls on page 36 critical points. Critical points are kind of the interesting parts of a graph. Over here, where it's kind of just increasing, that's not terribly interesting. But this point up here is interesting. And then I think another interesting point is right here. This is called an inflection point. If you're riding this graph as a roller coaster, that's the place where you stop going down and you hit like a bump. Okay, and you definitely feel that change of curvature as it stops curving kind of like concave and starts curving kind of more of in the convex and bubbles out. So that's an important point. There's ways to figure out those points. And then another important point is this point down here. This point up here is called a relative maximum. It's not the highest that graph's going to go, but between, let's say, this point here and this point here, it is the highest place that function goes on that particular interval. Same thing down here, this one's called a relative minimum. It's not the lowest point that this graph goes, but it's the lowest point in this general area. So it's called a relative maximum, or relative minimum. There's this other graph here that has an absolute maximum. It is the highest at this spot that this graph goes altogether. But then we've got another high point, and that's just a relative maximum. It's not the highest that it goes, but on a small interval here, the surrounding function, that is the highest place that it goes. And this one's another relative minimum. It's the lowest place on this little interval in this spot of the function, but it's not the lowest that this graph goes altogether. So you look at these and you're going to just say some general things about them. You're going to find out, at first you're going to estimate that high point, you're going to estimate that low point, and you could even estimate where it stops curving down and it starts curving the other direction. But who wants to estimate when you can find the real answer? Alright, so I made up this one here, and this is on the end spire, so this is for Willem. And if you want to analyze this sucker, you want to find that maximum, then we go over here, we're going to do a little analyze the graph. We want to find a maximum, and we slide this thing over and we say between here and here. And then right away it identifies the point there. It even puts a point, and it tells you what its xy values are. If you want to find that relative minimum, you're going to do the same thing. Analyze that graph at a minimum, and between here and here it finds the lowest point and identifies where that is and gives it a dot. And if I want to find this third one, I can do that too, but I'm not going to do that this time. If you've got your TI-84, this is kind of the old junky version, you can do the same thing. You guys have this button, you go to Secant, Calculate, and you got the same list of things here. So let's look for the maximum. And this time you get left bound and right bound. You can use your arrows. I think the new one draws a little line, but I put my little cursor a little bit to the left of the high point, and then I go my cursor a little bit to the right of it, and what it does is it puts two arrows up here and says between these two values, what's the highest value you get for f of x? And you can just hit enter again, and there you go. There's your maximum at the x and the y. If you want the minimum, same deal. You'll go to Secant Calculate, and now we're going to pick number 3, and we use our arrows, and we're going to put it so that at first our little cursor is a little bit to the left, and then we're going to scroll over to a little bit to the right of that point, and hit enter again and take a guess, and it'll identify, there it is, there's our minimum point. That x value, that's basically 0, and there's our y value of -1. So feel free to use that. You don't have to estimate everything, especially if your calculator can do it for you. Later on you'll learn a technique for writing another equation where you can check and find where the slope is 0 or where it crosses the x-axis. Right there, you know that that you've reached a high point or a low point. It's really cool way of doing stuff, and it doesn't require a whole lot of algebra. It's actually pretty easy. So okay, those are like some of the examples of some of the things in your lesson already. That's basically example 2 and example 3. Now let's talk really briefly about example 4. Example 4 is looking at something that we'll do more of later in the book called optimization. Some people have done like a build a better box kind of thing. We're trying to find the greatest volume. If you have a flat cardboard box and you want to fold up the sides and make a tray with a good volume. But optimization is a mathematical way of taking a situation and then finding the best possible answer. And so the real world example in the book, example 4 on page 38, takes you through somebody's orchard, which makes sense around here. And they have a couple of factors that they have to worry about. One is that how many trees can they put in their orchard. Obviously, the more trees you put out there, the more fruit you can get. But there comes a certain point where the more trees you put, the more crowded things get, and the less light each tree gets, and the less fruit each tree, on average, will be able to produce. So they're going to multiply these two things that they've cooked up. The first one here is 75 plus x. They've determined that right off the bat, they're going to have 75 trees, and then x indicates every tree that they're going to add. Okay, so obviously with the 75 plus x, that's going to contribute to a higher amount of fruit. Every tree they plant, obviously they're going to get more fruit. But the second piece here says that for every tree that they plant, it's 400 minus 2 times that number, that it's, it's going to be multiplied by that first number. And so if x gets really big, then you end up having a smaller number in the second piece that gets multiplied by the bigger number in the front. So there is going to be a sweet spot where you want x to be big, but you want to be so big that it starts to count against you and you lose fruit. So all I've done is I've typed it in exactly the way that they have it there in the book. I don't have to expand this into a polynomial or anything. I just leave it like this and then graph it. So I graphed it with more or less the same scale that they had in the textbook. And over here indicates that I haven't added anything because this is where x equals 0. And over here x equals 200, where that means 400 minus 2 times 200. That means this part equals 0, and I don't get any fruit. So I don't want that. That wouldn't make any sense. I want the highest point on this graph. So let's do a little cheating here. And we'll ask the calculator to go ahead and analyze that graph for a maximum. And I'll go a little bit over here, and I go this way, and there it is. It found it. That if x is 62 and a half, which ain't gonna happen, so we either plant 62 or we plant 63 additional trees, we're gonna get the highest amount of fruit yield out of this crop. So you see there, it's 3 times 7, 8. 3.78 times 10 to the 4th power. So that's a pretty big number, right? It's a lot of fruit. And that would be the sweet spot, no pun intended, for this fruit orchard, or to maximize their profit, to maximize the amount of fruit they're going to get. All right, sometimes you want that, sometimes you don't. But so they can use mathematical formula for doing this. Smart guys do this kind of thing all the time. They're always crunching numbers, and they want to find out. They don't want to waste money, and they want to maximize their profit. So there's a good way to do that. Okay, you just use what your calculator can do in order to solve these kinds of problems. Find that sweet spot, find that high point in this case of that graph, and look at the x value, and that's the value that you'd want to plug into this equation to maximize your output, get the highest number there. Okay, let's really quickly go back to your study notebook, and I want you to look down at the bottom of the page, and now that we've gone through these things, I want you to take just like 2 minutes and fill in those little spaces with the word bank that's on the side. You're probably going to want to hit pause here in about 10 seconds and do that work, and then I'll come back and I'll show you the answers there, and then we'll be done. The homework should be up on the board for you to take care of. Okay, here we go. We're going to scroll up and we're going to see what we got down here. So this points to the place where the graph is decreasing. We reach a minimum, and then the graph is increasing. It hits this spot, and now it's constant. Once it hits here, it's increasing again, and then reaches a maximum, and then it begins to decrease one more time. There's one bonus that's coming up in the next part of the lesson. That's a secant line, and a secant line cuts through the graph, and that'll be different than a tangent line, which will only touch this graph at one point. We're going to use that secant line to help us calculate slope, and that's coming up in our next episode. Hope this was helpful. If you need to, make sure you can go back and rewind to any point that you want to and see anything again. And yeah, good luck with that homework.